Hello everyone, today in this clip I'll be talking about section 6.3 in our textbook. It is about exponential functions and its property. So let's start with the definition of exponential function. Okay, 6.3 exponential functions. And then I'll show you some properties of exponential function. But first, let me give you the definition. An exponential function is a function that looks like this. An exponential function is a function of the form f of x equal to a to the x. Okay? Let's box that first. Okay? A here is people usually call the base number. Okay? And we have some condition for the base. A gotta be positive, and A gotta be different from 1. And let me explain the condition for you. A gotta be different from 1 because if you got 1 here, then the function is gonna be 1 to the x. And 1 raised to whatever exponent is always 1. Okay? And for A is positive. If A is negative, then we run into trouble. We have negative base, negative number raised to some rational numbers or irrational, like negative 3 raised to the 3.5. We haven't learned that yet, so we don't know what that is. It's run out to nearer. And even if A equals to 0, then 0 raised to something non-zero, so equal to 0. So we don't have a we don't have an exponential function anymore. We just have a constant come out. That's why we rule out all the weird cases. We put the condition for the base got to be positive and not equal to 1. Now we have exponential function. And I think the definition is pretty straightforward. Whenever you have a function where the variable x on the exponent, see, on the exponent, and we call it exponential function. And by the way, x here could be a positive number, could be a negative number, could be decimal, could be fraction, could be any real number that you want to plug in. So let me give you an example. Example, say f of x is equal to 2 to the x. So in this example, the base is 2. 2 is positive and 2 is not equal to 1, obviously. And x is the variable, the input, right? So this is an exponential function. Okay. F of 1 is 2 to the 1 equal to 2, right? F of 3 is 2 to the third power, which is 8. Okay. F of 0 is 2 to the 0. Right down here, which is 1, right? How about negative? F of negative 1 is what? 2 to the negative 1, which means 1/2. F of negative 5 is 2 to the negative 5, which is 1 over 2 to the 5th, which is 1 over 32. So forth and so on. Okay? Let me give you another example. I just base here 2, right? A whole number. How about this? Another example. Say f of x equal to 1/3 raised to the x. What is the base number now? The base is 1/3. Base 1/3. Is that positive? Yeah. Is that different from 1? Yes. So this is also another exponential function. Or you can write it this way: 1 over 3 to the x. It is the same thing. Okay. And you can try and see. F of 0 now is 1 over 3 to the 0, which is 1/3, so forth and so on. Let's extend the concept of exponential function a little bit more. Let me show you another version of exponential function. You can have this. Say f of x, another example, okay, equal to 2 to the x minus 3. So you see that what? Instead of having just x on the exponent, you have x minus 3. And as we learned about the what we call graph transformation before, you change from 2 to the x to 2 to the x minus 3. What did we do in here? We changed x to x minus 3. So graphically, you are shifting the graph. This is your original graph, right? You just shift the whole thing to the right 3 units because all you did was change x to x minus 3. See? Similarly, if I put what? X to x plus 3, change x to x plus 3, what does it mean? The graph is shifted to the left 3 units. Okay, let's recall back to what we learned before. Graph transformation. We move up and down, left and right. And you can actually apply it here. Okay, how about this? F of x is equal to 5 times 2 to the x. So keep in mind that this 5 right here doesn't have an exponent. Okay, so it's a constant 5 and times 2 to the x. Okay, so if you multiply a constant to the graph, what happened in here? You are stretching the graph by a factor of 5. So if the original graph is that tall, then 5 times taller. Okay, and we learned that before too. It's about what? Compressing or stretching the graph vertically. Okay, and actually many books define the exponential function this way: f of x equal to c times a to the x. And because I wrote this in here, so I give you a general form. So if you define the exponential function this way, then c here is 5 and a here is 2. Match up. But I claim that the original definition is like this. That should be more compact. And multiply by a constant is graphically like stretching or compressing. Okay? And we have to introduce this because in many applications that you may see in our textbook at our level, the C here is called the initial values. Why is that? Because initial values means when you plug in x equal to 0. See, used many things start with 0. So x equals 0, f of 0 is equal to c times a to the 0. And as you learned before, any non-zero number raised to the 0 exponent is 1. This is equal to c. Okay? So we start with times 0. We have c. So c here is a constant called the initial value. And a here we learned it already. It's the base number. Okay? So at our original definition, I didn't write c because this is the original one. So think of it as 1. Okay? And you can have any constant that you like. You have a new form right here. Okay? But I know that many of you guys are going to move on to pre-calculus and then calculus. So this is more like a definition of it. Okay? But you may see this quite often. A constant c times a to the x instead of just a to the x. But doesn't matter what, both are correct. Okay, and that is the definition. Let me move on to the second item. I'm going to be talking about some basic properties of exponential function. Okay, and in here I'm going to use graph to show you some basic properties of exponential functions. Number 2, properties. Okay, so let's start with an example. Say the simplest one, f of x equal to 2 to the x. Okay, let me sketch a graph of this thing, and then by looking at the graph, we can see some properties. X-axis, y-axis. Let me use, how about red color? Show you the graph. It's going to look like this. All right, right here, that one. Okay. So the domain of this function is all real numbers, from negative infinity to positive infinity. You can trace along the graph, along the red curve, you see what x could be from all the way from the left to all the way to the right. So negative to positive infinity. For the range, now the range, we're talking about the y value, right? It could go up forever, but it's not going down forever. The lowest value for y is still above the x-axis. So 0 to infinity. Okay? Not including 0. It's going to be something that bigger than 0. So with this function right here, doesn't matter what value you plug in for x, you will get something positive come out. Okay? And now, another thing, horizontal asymptote. Should be red, black marker. Horizontal asymptote. You see that this graph have a horizontal asymptote, which is the x-axis. The equation is y equal to 0, the x-axis. So you see what? Not just rational function that we learned before to give you the asymptotes. In here you have exponential function also can give you the asymptote. And in this case it is a horizontal asymptote. And in this particular example it's the x-axis. And then later on when you guys do the homework you see what the function could be shifted up, down, left, right, and the horizontal asymptote move up and down too. Okay. What else? Domain, terrain, the asymptote. Oh, okay. More. You see that this one right here, is it going up from left to right all the time? It's never change direction. Always go up. So we say that the function is increasing. Okay, this one increasing. And it's increasing according to what we learned from the previous sections. If the function is always increasing, you know that the function will be one-to-one. One-to-one. It passes the horizontal line test. Doesn't matter where you draw the horizontal line, it will intersect the graph at most 1 point. Okay? It's increasing one-to-one. And what is so special about one-to-one function? Back to the previous section, 6.2, we talk about something called the inverse function, right? So one-to-one function going to give you an inverse function. And for your information, later on in the next section, 6.4, we'll be learning about the inverse of exponential function, and we're going to call it the logarithmic function. Okay, we're going to learn that next time. Increasing one-to-one, yes, that's good. So via this example, we learned something about the exponential function. Domain, in this particular example, you see the graph looks like this, right? Domain from all real numbers, from negative to positive infinity. The range is like half of it, right? All positive number this time. And this has an asymptote, it's a horizontal asymptote in here, always increasing. And of course, increasing function will be a one-to-one function. Let me give you another example. See, this time I'm gonna show you the graph that's decreasing all the time. Okay, let's see. I'll leave that graph there. Draw another one. How about another example? G of x equal to, how about 1/2 raised to x exponent. Okay, so this example, I give you another exponential function with different base. Base now is just 1/2 instead of 2. And the graph of this function is going to be like this. X-axis, y-axis right here. Okay. Flip over the x-axis. Oop, I draw it too high. It's going to be like this. Okay. So one right here. And same thing, we're going to learn about some properties of this exponential function. The domain is still from negative infinity to positive infinity. Okay? And you trace along the x-axis, goes from all the way from negative infinity to positive infinity. Never stop. The range is still 0 to infinity. Okay? This time it's not increasing anymore. This graph is decreasing. The function is decreasing. Decreasing. Okay? And of course, decreasing function is always one-to-one. And this also has the horizontal asymptote at x equal to 1, y equal to 1. Y equal to 0, which is the x-axis. Okay. So pretty much, the idea is the same. We still have same type of domain, same type of range, and same type of asymptote. The only difference is what? The first one is increasing, the second one is decreasing. So what makes the difference? The answer is at the base number right there. Okay? So here is what? base is bigger than 1, not just positive, but greater than 1, and the function tends to get bigger. Okay, here the base is less than 1. 1/2 is just 0.5. You can think of it this way. This is 1 over 2 to the x. You see what? If I write this way, and you see the exponent now is actually on the denominator. Whenever you increase the x value, the denominator getting bigger, so the fraction gets smaller. The fraction gets smaller, the output gets smaller, right? And bigger x gives you smaller y, function is decreasing. Here it's just 2 to the x. A bigger x gives you bigger y, function is increasing. Okay? So, of course, you guys have more graph, you can what? Compress and stress and flip it upside down, flip it. Actually, this is a reflection of that graph about the x-axis, you see. Show it right here. Okay? You can compress the graph. The red one right here is the same thing as the dotted green one. You see, flip over the x-axis. Because this one, you can think of it this way, 2 to the negative x. Okay? So, we had the 2 examples. I'll show you some basic properties of the exponential function. It has the asymptote, which will always be increasing or decreasing. Domain tend to be all real numbers. And the range usually from a value to infinity, or you flip it upside down and from negative infinity to a constant somewhere. Okay? And let me move on to another topic in this session. We're going to recall some formulas that you guys are going to need to know for exponential functions. So how about number 3? Exponential formulas. I'm going to use a as a base number, okay, and n as exponent. So if you got a to the n, it's in general. So a here is a base, and n is the exponent. A here needs to be, well, what's the condition in here? Got to be positive, and yeah, that's good enough. Not equal to 0. And of course, actually in our definition of the exponential function, a needs to be positive, a different from 1. Because throughout the trivial cases, but in general, the formula is a to be non-zero. Be good. So a to the 0 is equal to 1. Okay? We don't have 0 to the 0. 0 to the 0 is undefined. That's why we need the condition as a is non-zero. And of course, this would be awesome if a is positive. Okay? And actually, I claim that a positive is more precise. I'm just looking at the textbook. It considers a is non-zero, but a needs to be positive for real exponent. Okay. So let me change this, make it better. The condition a is positive. Okay. A could be 1. Okay. So I have say a to the n times a to the m, where n here is the exponent, m here is the exponent. If you multiply the two fractions, two exponential formed together with the same base, you can add the exponent. This is a to the n plus m. And keep in mind that m and n could be any type of numbers, okay? Could be fraction, could be decimal, could be the whole number, could be positive, could be negative, could be 0, could be anything, okay? So, and a to the n, how about divided by a to the m? Now what? You subtract the exponent. You take the top one, subtract the bottom one. Bottom exponent, so n minus n. Okay. More a to the m, and then everything raised to the n, that is a to the m times n. I know that you guys learned this in middle school and high school already. I just rewrite the formula, just bring it back. Okay. If you got two bases raised to the same exponent, say n, this is a to the n times b to the n. And similarly, a over b raised to the n is a to the n over b to the n. Alright, more. So how negative exponent a to the negative n, and say you don't like the negative in front of the exponent, you can change it to 1 over a to the n. Okay, those are pretty much some properties of exponential equation or exponential expression. Okay, more. Let's make an asterisk. Okay, it's more like a theorem. It's pretty straightforward. So you have, if you got a to the m equal to a to the m, you have an equation where it's the same base a, and left hand side raised to the n exponent, the right hand side raised to the m exponent, and they equal to each other, then you can say that n is equal to m. Okay, looks trivial, right? But it helped you to solve quite an amount of exercises in our section. Say example, solve for x. You have something like 2 to the x plus 1 equal to, say, 8. Okay, how to solve x from here? Then you see that the left hand side is 2 raised to the exponent, the right hand side is just 8. So I can modify 8 a little. This is 2 to the x plus 1 equal to 2 to the third, because 8 is 2 to the third, right? Now I make the equation looks like a to the n equal to a to the m. Now, apply to our problem right here, I can use the property or the theorem right here. I can say that x plus 1 is equal to 3, because the left hand side exponent is n right here is x plus 1, and the right hand side is m is 3. So subtract the 1 both sides, I got x equal to 2. You see? Solve a problem like that. And something similar you see in our exercise in our textbook, homework, or my math lab as well. Okay. Next, another asterisk. Let me talk about a very special number that is very powerful. It's seen a lot in nature. It's called the E number, or the number E. So another asterisk, the number E. For now, we're gonna define E this way. Okay. First of all, we have an expression 1 plus 1 over n, and then we raise to the n exponent. Okay, where n is just any number, and this gonna get close and close approximately. Let me write this way. Approximately, not equal. Okay, approximately equal to E, which is what 2.7 1828, and then 1828 again, 2.7 1828, and this got the E number. Okay, as n approaches infinity. Okay, so what we're saying in here, whenever you set up the fraction 1 plus 1 over n raised to the n exponent, and then you plug in n with a very big number. Say you plug in n equal to a million, or some really big number, and you calculate the quantity, use calculator of course. 1 plus 1 over a million, everything raised to a million, you're going to come up with 2.71828. Okay, it's going to be a constant, and that's called E. Just like pi. Everyone knows pi, right? Pi is 3.14159. Da, da, da. Okay, now we have another number called E. And then it's go to infinity. It means what? We get n is very large. Okay. And that is pretty much about the section 6.3. So next time we're gonna be talking about section 6.4, which is the logarithmic function, and you will see that the log function is, log means logarithmic function. Okay, the log function will be the inverse of the exponential function. So you see it not much, because in here we just try to introduce you what it means by the exponential function. When you get to the homework, you see one type problem is trying to learn about shifting up and down and left and right, and determine the initial value C and find the exponential function. And then we're going to learn about log, and then We're gonna do exercises later on, I think 6.6. But for now, I think that's good enough for this section. Thank you for watching. I'll stop right here. And as usual, any question, please ask. Have a good day, everyone.